Alrighty. So today, in this unit, we're going to be focusing on area. We're going to go back to kind of like a little bit of geometry stuff, and we're going to be then. So today our focus is going to be, of course, on finding the area between two curves. All right, and then we're going to take that one step further, and we're going to take the area, okay, in the next couple of days. We take in the area and then rotating it about an axis to create a three-dimensional solid whose cross-section then would be that area kind of thing. Okay, so we're going to go three-dimensional here in just a few days. In fact, I think tomorrow, I guess, we'll be jumping into it, depending on how far. I think we should be able to finish this today, maybe. Well, we'll see. But we're going to get three-dimensional here, so it's going to be a little crazy, but, you know, we'll see how it goes, okay? But for right now, we're going to focus on just trying to find the area of a region between two curves, all right? So we are able to extend the application of definite integrals, okay, which is where we find the area under a single curve or between the curve and the x-axis, okay, to then extend that to find the area of a region between two curves, all right? So considering the following graphs. So if you look here in our kind of like progression here, we start with a graph that's got both f, okay, a function f, a function g, also graphed, and then an area, a region graphed, okay? Now, based on the region that's shown there, okay, what would be the appropriate integral? What would be the appropriate integral, for that region? In fact, let me just focus in on that one right there. What would be the appropriate integral to find the area of that region? The integral from what to what? A to b, right? Okay, those are our two x values of what? F, right? Okay, it's the area under f above the x-axis. So yeah, it'll be just f of x. Okay, so that's that one. All right. How about the second one then? What would be the appropriate integral for that region's area? Integral from a to b again of g of x, right? Because now it's g who is our boundary, our bounding curve there. Okay. And so then the question is, well then how do we find the area of just this region here? What can we do with these two regions to then yield just this region, which is between the area between these two curves here? Subtract them, exactly right. Okay, F contains both that region that we're interested in and G's area. And so if we subtract off G's area there, okay, then we get the area of this region right here. Okay, so it's equal to, of course, and if you want to put that all together in one integral, it's integral from a to b of f of x minus g of x dx. Okay, like that. All right, and that gives us the area of the region between the two curves, in this case from a to b. Okay. Now, it's important to notice here, right, that because this is subtraction, all right, order matters, right? If this was addition, right, for some reason, if this was addition, right, it wouldn't matter if I put g first plus f or f plus g. But since it's subtraction, that order matters here, okay? And so to kind of like help us figure out like what, which one we take and then which one we subtract from, you know, kind of that, the top curve minus the bottom curve, okay, is going to be our general kind of like guideline there, okay? We want to take the top curve and subtract the bottom curve, okay, or the greater curve minus the lesser curve. You can think of it that way too, okay? That will be our guideline as far as which one, you know, we take first and then which one do we subtract from that original, okay? So that's the idea. Questions on any of that? That's the main idea, okay? So then, definition-wise, here it is officially stated then, if f and g are continuous on the integral from a to b, and g of x is less than or equal to f of x for all x in AB. So here's that key thing again, right? If we understand that g is always less than or equal to f of x for all x in AB, then the area of the region bounded by the graphs of f and g And the vertical lines, x equals a and x equals b, is and is exactly what we just talked about right up there. The integral from a to b of, again, f is always going to be greater than g, and so it'll be f of x minus g of x dx. Okay, that is the area of our region right there. Okay? So, let's jump into some problems here then. All right. So, for example 1. Example 1 here says, find the area of the region bounded by the graphs of y equals x squared plus 2, y equals negative x, and x equals 1, and x equals negative 2. Okay. So, part of the battle here is just kind of figuring out what these regions look like. Okay, and kind of understanding those kind of pictures, I guess, so that we can then set up our integrals appropriately. All right, so let's kind of like do a sketch here maybe of this. Okay, so we've got the curve x squared plus 2. So let's see here. So 1, 2, 1, 1, 2, 2. Okay, so x squared plus 2, it's going to have an y-intercept there at 2. And then at 1, it'll have a coordinate of 3, and negative 1, it'll also have a coordinate of 3, and it's going to be just a parabola, so it's going to kind of go up, from there. Okay, nice parabolic shape. And then y equals negative x, well, that is a line, all right, okay, and it's got a slope of negative 1, y equals 0, so just something like, this. Okay, something like that. Oh, there you go. Okay, so far, just by graphing those two functions, all right, we don't quite have a region, right? There's no kind of like sectioned off finite area, right? But we still have two more boundaries here. We have x equals 1 as a boundary, and so I'll draw in maybe that as a dotted line here. Okay, and we also have x equals negative 2 as a boundary. I'll draw that in here. And so we can see then with those boundaries, and again with my rough sketch, now we have a finite region here, okay? And this is the region right here. Right? I'm going to shade it in kind of as lightly as I can. Okay? But there's that region whose area we're trying to find. Okay? So believe it or not, this is half the battle right here, is just trying to figure out what our region is, and so that way we can integrate appropriately and stuff like that. All right? So for our area here, okay, what will be our lower and upper limits of integration? What's going to be our lower limit of integration? From negative 2 to 1. Okay. What is our upper or top curve here? The x squared plus 2. Bless you. Minus, what's our lower curve? Negative x. Okay, and so there's our setup. Okay. There's our area. All right. And so then we'll go through this one here. So I guess, of course, now we have to integrate this thing, right? Okay, and let's do this one without a calculator. So which is not that bad. Let's see. A minus and negative x becomes plus positive x. So I'll go ahead and rewrite this as x squared plus x plus 2. Okay, x squared plus x plus 2 with respect to x. And so we integrate that, we get 1/3 x cubed plus 1/2 x squared plus 2x, and we're going to evaluate that from negative 2 to 1. Okay. And so we get 1/3 times 1 cubed plus 1/2 times 1 squared plus 2 times 1 minus 1/3 times negative 2 cubed plus 1/2 times negative 2 squared. Plus 2 times negative 2. Okay. And of course, if this is a free response question, you can stop and circle there, right, or simplify that arithmetic too. Okay. But again, just in the interest of time, I'm going to stop right there, and we'll continue on. Okay. But questions on any of that? Gabe, maybe? No? Okay. Emma?
What's the little dash above the X in the second row?
That is
Okay, cool.
just a thing there to make it even more confusing than it already is. Yes, Gabe?
So you just combine the two integrals, but could you have left them separated? Like the
Yes.
integral of x squared plus 2
Yeah.
minus
Yeah.
the integral of x.
You could have. Yep. Because again, you can break up an integral over addition, subtraction. So yep, absolutely. Okay. Everyone else okay? No? Okay. Oh, do you need the last step? Okay. Okay, so next then, we're going to turn the page here and again continue looking at the area of a region between intersecting curves. All right, so a more common problem involves the area of a region bounded by two intersecting graphs. So the idea here, right, if you compare it back to what we were just looking at, these graphs do not intersect. So there's no natural region created between the two curves. We had to include additional bounds here of x equals 1 and x equals negative 2 to then create a finite region. All right? Whereas, if we have intersecting curves, those can naturally create regions for us for the area, defined areas. Okay? So, again, like I said here, a more common problem involves the area of a region bounded by two intersecting graphs where the values of a and b must be calculated. Our lower and upper limits are going to be the intersection points, okay, of those graphs, right? So, again, we'll kind of like briefly sketch things here. So just as a sketch of what our graph's going to look like. Now, where we have 2 minus x squared, all right, we'll still have that vertical shift up of 2, but a negative x squared means you're going to kind of look something like this. Like I'm not going to be as precise here with this graph just because we're going to be finding these algebraically as opposed to graphically. Okay? And then the line y equals x is going to look something like that. Or I should say f of x equals 2 minus x squared. And then this should be g of x. Okay. Without our calculators, how can we figure out where these two graphs intersect to find our, because again, we create this region. Okay, there's our natural region that's created. So what should we do? Exactly, set them equal to each other. Okay, so to find our bounds, we're going to set f of x equal to g of x. Okay, and so 2 minus x squared equals x. I'll go ahead and move everything over here so it's equal to 0. So we're ending up with x squared plus x minus 2 equals 0. All right. This does factor to be x plus 2 and x minus 1. Okay. If it didn't factor, what would we need to use? Quadratic formula. That's right. Okay. But this one does factor, thank goodness. And so we get x equals negative 2 and x equals 1 as our bounds. Okay, so then to find the area of this region, we're going to be integrating from what to what? Negative 2 to 1. And then we need to do the top minus the bottom curve there. Okay, now it's clear because we have the graph which curve is on top. Which curve is on top here? Yeah, the parabola. So it'll be from negative 2 to 1 of the quantity 2 minus x squared minus x dx. But what if we didn't have the graph, or what if we couldn't come up with the graph? What could we do? Well, if to determine okay, so to determine here, is f greater than g or g greater than f? Exactly, plug in a point. But not just any point, it needs to be an x value between the bounds. Exactly right. So pick an x value between that negative 2 and 1. 0 probably is the best one, right? And we'll just, so again, use a value between the bounds. of -2 and 1. Okay. And again, I'm writing this out very explicitly. This is for notes, right? When you're doing the problem, you don't need to write this stuff out for your, you need to like write this out so explicitly, but obviously you're going to need these calculations when you're doing your own work on your own and stuff like that. So sure, we do f of 0, okay? What is f of 0? It's just 2, and we'll do g of 0, but g of 0 is 0, and so therefore f is greater than g, and so we're going to do f minus g in this case. Okay. I am not going to do the actual integral here because it's pretty straightforward, right? You could make this 2 minus x squared minus x and then just integrate this thing and of course then evaluate from -2 to 1. All right, I think we're okay with that, right? So just in the interest of time, I'm not going to actually solve that out, okay? Because it's pretty straightforward. All right. So that's the beauty of it on my part, all right? But we'll see. Hopefully you guys are feeling okay about that too. All right, so let's try another one here. Example 3. Find the area of a region bounded by the graphs of f of x equals -6 over 2x minus 4 and g of x equals x minus 6. So again, our goal here, right, we need to do area equals integral from a to b of the top curve minus the bottom curve. So we need to figure out our bounds, and we need to figure out what the top and bottom curve are. So again, to figure out our bounds, what do we do with our two functions? Set them equal. So -6 over 2x minus 4 equals x minus 6. Okay. To go about solving this, what should we do to both sides here? Multiply both sides by the 2x minus 4. So x minus 6 times 2x minus 4, and they're going to multiply out these two binomials. So 2x squared, let's see, minus 12x minus 4x, or minus 16x. And then plus 24. Okay, and then we'll add the 6 over so that we're equal to 0. So we'll have 2x squared minus 16x plus 30 equals 0. Factor out a 2, right? There's a GCF of 2. Always look for that GCF. It makes life easier when you're then trying to factor. Okay. So we need two numbers that multiply to make positive 15, but add to make -8. -3, -5, right? Okay, so x equals 3, x equals 5. Okay. Now, there's an x value here that could cause us some problems, but we luckily avoided it for our interval. What x value here would cause some issues? 2, right. What happened at 2? Our denominator for f would be 0, okay? And so we would go off towards infinity or negative infinity depending on the behavior there, okay? Thankfully, we avoided that, though, and so we don't have to worry about it. Remember, back to how we find these areas, right? F and G must be continuous on their particular intervals. All right, so we're lucky that that happened here. We avoided that interval, okay? In fact, we couldn't do this. We wouldn't be able to find the area if 2 was included in that interval. Okay, so anyway, we set it up here. The area then is going to be the integral from 3 to 5. And now I have to figure out which curve is on top, which curve is on bottom. So what's a good number to check? Ooh, is 0 a good one to check?
No.
0 is not in our interval, so we should not check 0. 4. Okay, so let's check 4. So again, top versus bottom. If 0 is in the interval, that would be a great one to check, but unfortunately it's not, so we have to pick something in between there. So let's try f of 4 and g of 4. Okay, so g of 4, that's easy, it's going to be -2. F of 4, let's see, it's going to be 8 minus 4, so 4, -6/4, which is equal to -3/2, which is equal to -1.5. Okay, so which one's greater? Very good, right? Okay, -1.5 is a higher value than -2, right? Okay, -1.5 is less negative, so it's a greater value, all right? So it's going to be -6 over 2x minus 4 minus x minus 6 dx. Okay. And this one I will not be integrating for you guys, but I will kind of give you some recommendations here. So, for example, to integrate this, we'll need to use what? U substitution. Okay, so in other words, we'll need to kind of split the integral up. Integrate this using a U substitution and integrate this as normal. Using the power rule. Okay? So you kind of have to like split the integral. Okay, split up the integral there and integrate those separately. One using a U substitution, one using your normal power rule. Okay? You could try and combine these two things together using getting a common denominator and stuff like that, and then maybe doing some like long division. But I feel like that's going to make it harder. In fact, no, the long division will put you kind of back where you are. Not as bad, but anyway, yeah, I think the best way to go there would be to use a break it up. Okay, questions on that so far? We're all good? All right, now let's take a look here. Example 4. What do you notice about how this one is set up here? Just the setup. Okay, that's true. That is one difference, and we don't actually have to solve it. But what else is unique about the curves? Yeah, they're in terms of y, not in terms of x. So what do you think that's going to affect? How's it going to affect our integral? Instead of integrating with respect to x, we're integrating with respect to y. That's right. Okay, so these are in terms of y. Okay, we can sometimes transform things that are in terms of y back to in terms of x. Okay, for example, this second curve is pretty easy for us to translate that to be in terms of x, right? You just subtract 1 from both sides. The first one, it can be done, right? We'd have a plus or minus, though. It'd get a little bit tricky. And so sometimes it can be helpful to translate things back in terms of x and try and integrate that way. But in this case, we're going to leave it in terms of y, because that can also be easier too. In this case, I think it's going to be easier to do it this way. All right, so let's kind of sketch a graph of what this is going to look like. Okay, so we'll get our coordinates there. Now I'm actually going to make like a little table here, like an XY chart. Okay, like a little T chart there to help us out. Sorry? I guess I could have done it that way, yeah. So, but then it also gets confusing because you're like x and y coordinates when you're going to go plot them in reverse from what you're used to as well. So anyway, so we'll plug 0 in for y because, 0 is a good number to start with. And so it'll be 3 for your x coordinate. Okay. If I plug in 1 for y, 1 squared is 1, 3 minus 1 is 2. If I plug in negative 1 for y, negative 1 squared is 1, 3 minus 1 is 2. Okay, so let's see here if I can get some decent looking graphs here. All right, so 3, 0, 2, 1, 2, negative 1. Okay, and so we're going to basically end up with like a parabola here. Let's see here. 0, yeah, okay, square root of 3. So it's going to be something like that. Okay, something like that. And then x equals y plus 1. Again, I guess you could just rewrite that as y equals x minus 1 and graph it that way. But anyway, negative 1, I'll put that in for y, so it's going to give us an x of 0. Let's plug in 0 for y, and I'll get 1. 1 in for y gives us 2, and 2 in for y gives us 3. I kind of ran out of space there, but okay. So we'll plot those points. So 0, negative 1, 1, 0, 2, 1, aha, we see a point of intersection there. Okay, so something like that. So we can see our region here. Okay. And so we also need to shift kind of like our orientation as far as like how we designate our curves, okay? It's no longer top and bottom. We deal with top and bottom when we're integrating with respect to x. But since we're integrating with respect to y, how should we kind of shift our thinking? Not top minus bottom, but Yes, right minus left, okay? Right minus left, because it shifts now that we kind of changed our orientation there. So now it's going to be right minus left, okay? So now the area here is going to equal the integral of a y equals a, y equals b of right curve minus left curve, okay, dy. You can see some of the complexity if we were trying to integrate this with respect to x. If we were trying to integrate this with respect to x, which we could do, what's going to be true about our top curve? It's not always the same top curve, right? Okay, and we're going to talk about what happens there in just a little bit. But you'll see here, for this region, right, the top curve is the linear function x equals y plus 1 for this portion of the region. But then once I go beyond this x value of 2, the curve, the top region is the positive version of this right here. Okay, the bottom curve stays uniform. It's the same curve all throughout. But as you move left to right in the region here, it's going to change the top curve. Which is why we can avoid that though if we think instead of right minus left. The rightmost curve is always that parabola-like curve, and the leftmost curve is always that linear curve. So it creates an easier integral to set up. Okay, so again, it looks like we intersect at y value of 1. Again, we're looking at the y value here. So yes, it's x value 2, but it's the y value of 1. It looks like we intersect at that y value of 1, but I'm not quite sure what the y value is down here. How can we figure out exactly where these two things intersect? Set them equal. Set them equal. 3y minus y squared equals y plus 1. I'll add the y squared over and subtract the 3, so we get y squared plus y minus 2, okay, equals 0. It does factor y plus 2, y minus 1, and so y is equal to negative 2 and y is equal to 1. Okay, and so in fact we're going to integrate from negative 2 to 1. Again, remember here, 1 is the y value of that point of intersection because our integral is with respect to y. Negative 2 is the y value of the point of intersection. So my curve here, you can see, is not super accurate because there's my negative 2, and I've already said they intersected. Anyway, okay, the right curve is that 3 minus y squared. Excuse me, the left curve is the line. And there's our answer. Okay, and again, I leave it to you. We're just setting it up. Okay, it just says set up. But that, again, you integrate that like you would if it was x's instead of the y's there. Okay, at this point, it's just a matter of now integrating and plugging in and stuff like that. Okay, moving on. All right. So, number 5, set up the area of the region bounded between these two graphs. All right. So, again, to find our bounds, what do we need to do? Set them equal to each other. So we have, let's see here, 3x cubed minus x squared minus 10x equals negative x squared plus 2x. Okay. And so let's get all of our terms together here. So let's see. It looks like I can add the x squared over here. So it'll be 3x cubed. The x squared is going to cancel, and then I'll have a minus 12x equals 0. Okay. And so I can factor out a GCF of 3x here, leaving behind an x squared minus 4, or in other words, x minus 2, x plus 2, right? That's a difference of squares there, that x minus 4, so it does factor. So you get x equals 0, x equals 2, x equals negative 2. Whoa, 3 bounds. Three bounds. Can't integrate 3 bounds. So let's take a look here at what's going on. What do you guys think is happening here? Life. Well, see if it'll show up on my graphing calculator here. Yes, it do. Okay. And let me maybe adjust my window here. So there's our first curve, F, and there's G. Okay. We're getting 3 bounds because we have how many regions created by these intersecting curves? 2 regions are being created. We have this region right here. We have this region right here. Okay? So, how many integrals are we going to need to represent this total area? We're going to have to do 2 integrals. One integral for this region plus the integral for the area for this region. Okay? So, let's go ahead, though, and proceed as we normally would. All right? So, maybe I'll rewrite these in numeric order here. And let's see, again, is f versus g here, which one's greater, right? We'll do it first for the interval from -2 to 0. Okay, so what would be a good value to pick between -2 and 0? Between -2 and 0. -1. Okay, again, if we pick 0, we know what we're going to get. We're going to get the same value in each case because we know they're equal at 0. So we want to pick something that's not. So we'll pick f of -1 here. We'll do f of -1. We'll do g of -1. Okay, f of -1, well, let's see here. It's going to be -1 cubed times 3, so -3. -1 squared, so -1, and then plus 10. And so that's going to be, well, 6. Okay, and then g of -1, it's going to be -1 minus 2, so it'll be -3. So f is greater than g on the interval -2 to 0. F is greater than g, which we can confirm here with our calculator, right? That's f, and it is above, and there's g, it is below. Okay. Bless you. And again, we'll do the same thing here for the other interval from 0 to 2. Okay. They won't always alternate. Okay, so please don't assume, well, Mr. Whitmire, if f is greater than g here, then certainly g will have to be greater than f for the other one. Don't assume, okay? It won't necessarily happen. Sometimes it comes down, touches it, and goes right back up again, above it. So, again, we'll check, though, just to make sure. In this case, they do alternate. So it's going to be 3 minus 1 minus 10, and this will be -1 plus 2, so we get 1 there, and then we get -2, -12. Oh gosh, no, did I mess up that calculation here? 3 minus 1 is 2. Minus 10 is -8. There we go. Okay, so now in this case, g is greater than f. And so our area will be the integral from what to what? -2 to 0 for that first region of, and I'm just going to write, if you'll permit me here. Okay, rather than writing out all the entire function, I'll just do that. And then plus the integral from what to what? 0 to 2 of what? G minus f now. Okay, just like that. G minus f, yes.
So if f was greater in both cases, could you still do 1 or do you still need 2?
F was greater in both cases. You could just do 1 then. Yes, you could just do 1. Will it be wrong if you broke up into 2? Nope. It'll still be okay to do it that way as well. But yeah, you would just need the 1 then. Good question. Did everyone follow that? Okay, again, if f was always on top, so if in both cases f was on top, you would only need one integral for that. You wouldn't have to break it up into 2.
Wait, so what would that look like for this one?
You would, if f was always on top, you're saying, what would it look like? Then you would integrate from -2 to 2, f minus g, top minus bottom. Okay, that's all it would be. All right, so there's that. All right, number 6. All right, let's take a look at this one now. Okay, write an integral expression that represents the area of a region in the first quadrant, bounded above by the f of x equals the square root of x, and below by the line g of x equals x minus 2, and the x-axis, okay? Which is kind of a redundant thing to say because it says a region in the first quadrant, so we don't necessarily need that, but anyway. So, let's sketch this out. Okay. Oh, no, x minus 2, so 2. Okay, so I'll graph the square root of x, okay? At 0, it's 0. At 1, it's 1. And then at 1, 2, 3, 4, it's 2. so there's that. And then I also am going to graph the line x minus 2. So that's a negative 2 y-intercept. And then up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. Oop. Okay. So here's where it gets a little bit tricky about trying to define that region. Okay, you might be tempted here to start saying this whole thing is our region, but it is not. Okay, remember that we are bounded by the x-axis as a boundary. We're also bounded by the square root of x and the line x minus 2. And again, for further emphasis, we're in the first quadrant only. So should I include this area here? No, it's not in the first quadrant, okay? So I'm going to exclude that. So what region are we talking about? Well, here's a region that is bounded both by the square root of x, by the line x minus 2, and the x-axis, right? This region right here includes all of those as boundaries. That's in the first quadrant. That is our region. All right. Now, in this case, one function is always on top. Okay, what is the one function that's always on top here for this region? F of x. But two different functions, okay, are on the bottom. Right? What are our two different functions that are on the bottom? G and y equals 0. Exactly right. Okay? Y equals 0, and then g of x, which is y equals x minus 2, or g of x equals x minus 2, that kind of thing. Okay. How do we accommodate this to find, excuse me, the area of this region? So, Jake?
Wouldn't you take the full integral from 0 to 4 of root of x, and then you minus the integral of 2 to 4 of x minus 2?
So, that would work, yes. All right, so let me write that up here. Let me write that up. So you said integral from 0 to 4 of what minus what?
I just did of root x.
Root x? Oh, you did, oh, okay, I see what you're saying. And then you did minus the integral?
Yeah.
Okay, actually, so then it's not quite right. If we did this, let me see here, x minus 2 dx. Okay, if we did that and then subtracted off the integral from 0 to 2 of x minus 2 like that, that should work. But that's more complicated than I was looking to do here. Okay, that's more complicated than I was looking to do. We're going to break this up into two regions. Okay, where the top and the bottom curve change. Well, that's how we'll determine our integral. So the first integral we'll do is the integral from 0 to what? To 2. Okay, again, we can kind of visually see that there. Okay, the integral from 0 to 2. What's our top curve in that case? Square root of x minus the bottom curve, y equals 0, so it's just 0, right? You don't even have to put that in there if you don't want to, but. Okay. And then we'll add to that the integral from 2 to 4. And our top curve in this case is still square root of x, but now minus what's our bottom curve this time? X minus 2 dx. Okay? And so that maybe is the easy way to see it there. This will work, though. Okay, this will work. I'm pretty sure. I'll have to check that. I think it should. Yes. Okay. All right. I guess we'll call it there. I don't want to push things too much. All right. We did almost finish up. Okay. The homework will be on Google Classroom, so you can check that out. Okay. There's also a new problem set for you to be working on, so make sure you're checking that out as well. Okay. And then tomorrow we'll talk about Solids of revolution. Huzzah. Okay. Yes.
Can I use my extra time for the FRQ?